Hello, and welcome back to the Science of Concrete Materials class. This is lecture number 34 of the class, and today we will start on a new module, which is the testing of hardened concrete. In the previous module, as you recall, we studied how the concrete responds to stresses, which explained the behavior of concrete under stress and the factors that impact such behavior or response. Today we'll talk about the testing of the hardened concrete. So in this module we will discuss the following. Why do we test concrete? Why do we need standardized testing for concrete? The significance of testing, and we'll also talk about the various types of testing, namely the compressive strength, tensile strength, flexural strength, the modulus of elasticity, and we will also discuss some of the non-destructive testing methods, why they are used for, and what are they and why they are used. Okay? So, why do we test concrete? There are a number of reasons for carrying out tests on hardened concrete. On a fundamental level, tests can be used to investigate the physical laws governing the mechanical behavior of concrete. Such tests would be used to help deduce and verify the relationships described in the previous module between the physical and mechanical properties of the constituents of the concrete and the elastic properties and strength characteristics of the concrete made from those materials. Second, often these physical laws may not be fully developed or understood. In this case, a second type of testing is used to determine the mechanical properties of a particular type of concrete in some specific applications. This is basically done by simulating the expected conditions of use for a particular concrete as closely as possible and observing the performance of the concrete. These results will not be fundamental in that it will usually not be possible to extrapolate them to predict the behavior of different concretes under different service conditions. Okay? On a simpler level, though, a third type of test would be carried out when the physical laws governing the behavior of concrete are known, but there is a need to evaluate the physical constants, such as the modulus of elasticity. Okay? Finally, and most commonly, routine information on the quality of concrete may be required. So this type of testing usually goes under the name quality control testing. Here, extreme accuracy of measurements is less important, but the speed and ease of carrying out the tests might well govern the choice of test procedures. Okay? Although the tests to be described in this part of the class are generally in the category of quality control tests, they are often used for the other three purposes mentioned just above. Okay? So, before really describing the concrete test methods in detail, there are two other very important concepts that must be discussed. First, the need for standardized testing. Okay, the strength, durability, and other mechanical properties of concrete should not be considered in any sense as, fundamental or intrinsic materials properties. Such variables as the specimen geometry, specimen preparation, moisture content, temperature, loading rate, and the type of testing machine and loading fixture will all affect the observed mechanical behavior. So Different test procedures would be expected to yield different results, and experience has shown this to be the case. So, when defining some mechanical property, such as compressive strength, it is also necessary to specify the test methods used in determining the strength, okay? To really complicate matter further, there are generally no unique relationships between values for mechanical properties measured in different ways. So, for example, we measure the compressive strength of concrete using two specimen shapes, cylinders and cubes. The ratio, between cylinder strength to cube strength will not have a constant value, but will vary dependent on the type of concrete. So you always have to remember that. So to try to minimize the confusion that would result if everyone were to use different test procedures, various standard test methods have been proposed. For these procedures, the test parameters are rather arbitrarily fixed so that different people working in different laboratories in different areas can nevertheless carry out comparable tests, and so can generalize these test results, okay? The standard test methods most commonly used in North America are those developed by ASTM, and these will be described in detail here. But some agencies, such as the US Bureau of Reclamation, for example, may use somewhat different procedures. Also, most European countries have their own national standards. So you have to be familiar with that maybe, and you always have to refer the tests is reported under which standards, okay? Also, it should be noted that as cement and concrete technologies change, the standard test methods also change. All test methods are abandoned or modified, and new test methods developed. For instance, it is estimated that about 1/3 of the ASTM tests are revised annually. That's a lot. That really signifies the rate at which the cement and concrete technology is really changing. Finally, there are properties of concrete, such as impact strength, as we will discuss later in the non-destructive testing. For this property, no standard test methods have been yet developed. So properties, as properties become important design characteristics, completely new tests have to be established, for their determination. That's all. The point of this, there is always a need to develop new standardized tests for use. Okay, so the second concept is the significance of testing. It must be emphasized that concrete tests are in general carried out not on the concrete actually in the structure, but on a small companion samples of concrete that is supposed to represent the quality of the concrete in the structure. Unfortunately, this can cause a great deal of confusion. Usually when we talk about the strength or the mechanical properties of concrete, we are referring to the strength of concrete in the structure at some given age. But what is really measured is the strength of small test specimens. So many studies have shown that there is not a particularly good correlation between the strength of concrete defined by the ASTM standards and the strength of concrete actually in the structure. This discrepancy arises from differences in the many variables that determine the behavior we just mentioned. Although standard tests may well give some indication of concrete quality, many problems have arisen where concrete samples gave acceptable test results while the concrete in the structure was of lower quality and behaved quite differently. Conversely, there were also some cases where perfectly good concrete structures have been repaired on the basis of standard tests given unacceptable values. Okay, so their experience have shown both situations to occur. An example really of how the discrepancy between real and measured concrete property arises. Let us examine the compressive strength. So the concrete in a standard cylinder is subjected to different compaction effort from the concrete in the structure. Also, the size is different from the size of the structural member by several orders of magnitude. The temperature and relative humidity of curing are different. Also, the cylinder remains free of stress until tested, while the structural members will be carrying at least some load. Okay, they'll be under load. So the concrete in the structure may be at least partially restrained by steel reinforcement or by other structural members, for example. Okay, so in view of this, it would be surprising if the cylinder strength did accurately reflect the strength of the concrete in the structure. Okay, so just keep that in mind. So as a result of this, standard tests carried out on small, supposedly representative samples do not in any way guarantee the quality of concrete. Rather, concrete design is based on the implicit assumption that if the concrete has been placed, compacted, and cured properly in the structure, and if the test results are satisfactory, there is a very high probability that the material in the structure will behave in an adequate manner. Okay? That is the approach. This is quite different from the common assumption that we actually know or measure. So the mechanical properties of the concrete in the structure. Also, material properties used in design are obtained from standard tests. So the design procedures used in countries having different test methods must also be somewhat changed, or at least must be different material constants in the design equations. Okay, so that you have to keep that in mind. At this point, after all that, one might well ask if the concrete or if the properties we measure are not necessarily representative of the concrete and the structure. Why bother to test the concrete at all? Okay? The answer to this question is that there are some very good reasons for doing so, but that an accurate measure of the properties of the concrete in the structure is not one of them. Okay? But the reasons are as follows. First, tests can help ensure that concrete was batched properly. That is, the proper ingredients in the proper proportions were used and that the laboratory mix design was adequate. Okay, so that's a good reason to test. Second, they can indicate the statistical variability in the properties of the concrete being produced. High variability is one indication of poor concrete practices. Third, they may reveal problems arising due to inadvertent changes in materials or environmental conditions. Fourth, the simple existence of an extensive testing and inspection program will help ensure that the people involved in the production, delivery, and placement of the concrete do not become lax or careless in their operations. So basically that forces people to be accurate and do their job. Number 5, if, in spite of all precautions, structural problems do arise, the properly carried out undocumented test reports will help, to pinpoint the problem. And again, good documentation of the testing and the inspections will help us, investigate or pinpoint where the problem occurred, should a problem occur. Finally, test results may be needed before further construction operations can be carried out. For instance, strength tests may be used as a guide for the time of form removal or for the stressing of the pre-stressed concrete, pulling the post-tension cables, for example, something like that. Okay? So I hope this introduction, helped really clarify in your mind why do we test concrete and how, the standardized testing and what is the significance of testing, all that. I hope this introduction, helped you understand all that. Okay, so let's get, to the testing that carried out, and the first we will start with the compressive strength. By far, the most common test carried out on concrete is the compressive strength test. Okay, there are several reasons for this. First, it is commonly assumed that most of the important properties of concrete are directly related, or at least qualitatively, not necessarily quantitatively, to the compressive strength. Okay, though this is not, always true. Okay. Second, since concrete has, very little tensile strength, it is used primarily in a compressive mode, and therefore it is the compressive strength that is important in engineering practices. Third, the structural design codes are based mainly on the compressive strength of the concrete. And number four, the test is easy and relatively inexpensive to carry out. Okay. The compressive strength test, and in particular the experimental variables that may affect the results, are described subsequently in detail. It should be remembered that the experimental variables discussed in terms of the compressive strength will also have similar effects on other mechanical properties of the concrete. Remember this statement. Okay. Okay, so if we look at the ASTM cylinder test, which is ASTM C39, as we indicated in the previous section, the test for compressive strength is so sensitive to variations in procedure that it must be carried out strictly according to standard procedures, so that results from different testing laboratories or even within the same laboratory are comparable. Okay. Therefore, the ASTM test, is described in some detail here so that you're well aware of it. The normal compressive test specimen in North America is a cylinder with a length to diameter ratio of 2:1. Usually the dimensions of 150 millimeter diameter or 6 inch and 300 millimeter or 12 inch long. The specimens are prepared and tested as follows. Okay. The molds. The ASTM requirements for molds, which is per ASTM C470, are not really restrictive as to the materials that may be used for concrete molds. As long as the molds are non-reactive with concrete, are watertight and sufficiently stiff so that they do not deform excessively in use. Okay, there are two basic types of molds. The reusable molds, usually made of heavy gauge steel or rigid thick-walled plastic. Second, the single-use molds, usually made of formed sheet metal, waxed cardboard, or thin-walled plastic. Okay. In general, the single-use non-rigid molds are can result in somewhat lower strength, typically about 3%. Okay. And also they will probably result in a higher standard deviation. Okay. This is in part because of the top ends of these molds often take on somewhat oval shape, and in part because some of the applied compactive effort, like the rod or vibration, goes into deforming the mold rather than just consolidating the concrete. Okay, so while the somewhat lower strengths obtained, with the single-use molds are not of much importance, for normal concretes, they can be significant for very high strength concretes, above 100 MPa. So basically, the selection between single-use molds and reusable molds, this goes back to the concrete practitioner and his experience. But as I said, care must be taken when dealing with high-strength concrete. Reusable molds should be avoided. Okay, so how do we mold the specimen? This is basically described in ASTM C31. The mold is placed on a firm level surface free from vibration, from a representative sample of concrete. The mold is filled in layers, dependent on the method of consolidation. So if the slump is more than 75 millimeter or 3 inches, the concrete is consolidated by rodding. If the slump is less than 25 mm, the concrete is consolidated by vibration. If you refer back to the testing lecture early on in the first module, okay? For the slumps between 25 and 75 mm, the specimen may be consolidated either way, okay? So the specifications, for a particular job may require certain method of consolidation. Always consult your job specifications. Before you look at ASTM, look what the specification says. If the specifications refers you to a particular ASTM standard, you follow that. If it lists, for example, more stringent or different requirements, you have to follow that, okay? So, and again, we said you have to follow, your job specifications if for any particular consolidations. The reason, for these alternative methods is that, poorly compacted cylinders will have lower strength than will a properly compacted one. So the method of compaction and following the standards is key. For stiff mixes, though, which will always be compacted by vibration in the field, Hardened simply will not compact the cylinder sufficiently. So remember that. For lower slump concrete, Hardened will not do it. Okay? And again, do not use, for example, vibration with wet or high slump mixes, as this will cause segregation. Okay? And again, okay, so if the specimen is to be rodded, in the case of Hardened, it should be filled in 3 layers, 3 equal layers. Each layer is rodded 25 times with a 16 millimeter diameter steel rod with a rounded end. For the upper layers, every time you place an upper layer, the rod should penetrate at least 25 millimeter into the previous layer, okay? After rodding each layer, the mold is tapped lightly 10 to 15 times with a mallet, okay? Or if it's not a mallet, maybe you use your open hand in the case of the light gauge molds. In the case of the heavy gauge mold, you have to use a mallet, okay? Basically, this, will close any holes left, after rodding. In the case of the specimens to be vibrated, they are filled in 2 equal layers. Either, internal or external vibration may be used. After consolidation, the top surface is finished, by striking off with the tampon rod or with a trowel. Okay, that's how we mold the specimen. Okay, curing. This is important. Cylinders, are made primarily for 3 reasons. 1, to check whether the laboratory design mixes achieve the specified design strength, as the basis for acceptance or for quality control. 2nd, to determine when the forms can be safely removed. 3rd, to determine when a structure may be put into service or when the pre-stressed concrete members can be tensioned. So cylinders are also used for comparison with results from in-place tests and to determine the accuracy of field curing and protection of concrete. So the curing conditions of the cylinders depend on the purpose for which they were made. And again, in certain cases, for example, like when we use, especially when we use the cylinders to determine when the concrete members can be stressed, I would advise these cylinders to be placed, stored, and cured in the same exact manner as the concrete member in question. Okay, that will help eliminate any other variables that could happen and really compromise or impact the test results. Okay. After that, the capping of the cylinders. So cylinders, as I said, cast as just described, will have end surfaces, particularly the top surface, that are rough and not necessarily plane or parallel. So if tested in this condition, the apparent strength of the concrete would be considerably reduced as a result of the stress concentrations that are introduced on loading. If we have a convex end, will lead to a lower measured strength than, for example, concave end. Okay, because the stress concentration introduced are more severe. So it is required that the specimen ends must be plane within 0.05 millimeter or 0.002 inch. So one way to achieve plainness is by grinding the ends. This is satisfactory, but it is expensive and time consuming, and quite frankly, I will not guarantee the results 100%, depending on the operator who is doing the grinding. So this one is used mostly with high strength concretes, although some laboratories use this technique routinely for all concretes. But the person who is doing this is going to be highly qualified, and it has to be accurately done. Okay. The most common way of achieving this, plainness required is to cap the ends of the cylinders, according to ASTM 617, with a suitable material. So 3 different capping materials are permitted. First, a thin layer of stiff Portland cement paste may be used on freshly molded specimens. Okay, or maybe on hardened cylinders, either high strength gypsum plaster or sulfur mortar may be used. Okay, the sulfur mortar being much more common though, as the sulfur mortar is prepared by heating it to about 130 degrees Celsius and then pouring it into lightly oiled steel capping plates. Okay, the cylinders are then set into the sulfur in such a way that the cap's end being about 3 millimeter thick. Okay, and then are aligned so that the deviation of each cap from perpendicularity with the axis of the specimen is less than 0.5. Okay, so that's really what the method, as I said, mostly used, but again, grinding for high strength concrete, but it has to be done accurately and by a very experienced person. Okay. Okay, so how do we determine the compressive strength? And again, as I'm talking about the tests according to ASTM C39. Once the specimens have been capped, they are ready for testing. The tests may be carried out in any suitable testing machine. Basically, the description of the apparatus is 2 hardened bearing blocks are used, a solid one that the specimen sits on, and a spherically seated one that will bear on the upper surface. These blocks must be plane to within like 0.025 millimeter. Okay, for the 150 millimeter diameter cylinders, the maximum diameter of the spherically seated block is about 255 millimeters. Okay, care must be taken to ensure that the ratio of the maximum diameter of the bearing block to that of the specimen does not exceed the values given in ASTM C39. Okay, so a bearing block that is too large will generally lead to compressive strength values that are too high. Okay, so because strength is dependent on the loading rate, the specimen is then loaded at a controlled rate of like 0.15 to 0.35 MPAs per second, or 20 to 50 psi per second. For hydraulic machines, this is for hydraulic machines, or maybe at a deformation rate of 1 millimeter per minute, for mechanical machines. Okay, depending what type of machine you are using. Of course, loaded until failure, which is defined as the maximum load the specimen can carry. So the maximum load and type of failure, after that, they are reported. Okay. A photo of a typical testing machine and the bearing blocks are shown here in this photo. Okay, that was for testing the cylinders. Okay, if you hear me mention something about testing cubes. Okay, cube tests are used as the normal compressive tests in the UK, Germany, and some other parts of Europe. The British standards require basically 150 millimeter cube, 6-inch cube mold, which is filled in 3 layers, each layer being rodded 25 times with a 25 millimeter square rod. Alternatively, the cube may be compacted by vibration. Okay. After that, it is handled in much the same way as the cylinders as we just described above, except that the storage temperature is different, about 20 plus minus 1 degree Celsius. Okay, the cube is tested at right angles to the position at which it was cast. This means basically the faces of the cube in contact with the bearing platings were cast against the sides of the rigid steel molds, and we ensure planeness in this way. Okay, so the bearing forces are sufficiently plane, as this will require, I said, no capping or grinding. Okay, this is actually one of the advantages of using cubes for compressive strength testing. Okay. After that, the specimen is then loaded at a rate of 0.25 MPa per second, or 33 psi per second, until failure, of course. The main drawback of the test cube is that the friction between the platings and the specimen ends create much more confinement or triaxial compression in the specimen than in the case of the larger cylinder specimens. Okay, we will discuss this, and we discussed it in the previous chapter, in the previous module, and we will discuss it again here. Okay, this fact here leads to a higher strength value when measured on cube basis rather than in the cylinder. Keep that in mind. Okay, there have been reported a ratio between cube strength and cylinder strength, which is commonly assumed to be about 1.25. The ratio, again, is not in fact a constant one, which ranges from about 1.3 for low strength concretes to about 1.04, as you can see on this graph here. 1.04 for higher strength concretes. Okay, so this ratio, if you want, again, I've seen concrete professionals and people use this ratio. I will not, although maybe some standards report a ratio, I will not use a ratio arbitrarily unless there is evidence this ratio has been actually calculated from actual data on the concrete I am using. Okay, so that's something I have to warn you about. Okay, so we talked about the cylinder, compressive strength, ASTM C39. We talked about the cube test. The reason I covered the cube test because, you know, sometimes in different parts of the world other than the US, the concrete is reported based on cube. You have to be familiar with that. So, but again, converting between the two must be done with care. Okay. Let's really talk about the factors that affect the measured compressive strength. You heard me talking about variables and how they impact. Let's talk about these variables and what they are. Okay, so just to repeat, the compressive strength test, you know, we just described, appear to be, you know, perfectly straightforward, okay? But unfortunately, the results obtained can be affected, as I just said, by many variables, and this effect can be really considerable. So if we are to be able to interpret strength values obtained by the standard, but, you know, arbitrary, you have to keep that in mind. These procedures, it is necessary to examine in detail how the compressive strength is affected by the test parameters, okay? The first parameter is the stress distribution in the specimens, okay? The compression test assumes, you know, a state of pure uniaxial compression. Remember previous discussion. But this is not really the case because of friction between the ends of the specimens and the platings. So this frictional force arises from the fact that because of the differences of the modulus of elasticity and Poisson's ratio of the steel and the concrete, so the lateral strain in the platings is considerably less than the lateral expansion in the ends of the specimens, okay? So if they were, you know, free to move, as you have to keep that in mind. So through friction, the platings act to restrain the lateral expansion of the ends of the specimens and to introduce a lateral confining pressure need at the end of the specimen, okay? So this confining pressure, which also introduce shear stresses, by the way, is greatest right at the specimen ends, you know, and it gradually, you know, dies out at the distance from the end, approximately, for example, a distance equal to square root of 3/2 of the diameter, okay? So that is something you have to keep in mind. All right, so the exact nature of the stress distribution basically depends on the type of the contact between the specimen and the platings for that particular test. So the manifestation of this lateral confining pressure is often, you know, the appearance of relatively undamaged cones, you know, or pyramid shape of concrete, you know, and the concrete specimens tested until it's, you know, when tested to failure, okay? As you can see in this figure right here, okay? So for a standard cylinder with a length to diameter ratio of 2, only a small central portion of the cylinder is in true uniaxial compression, you know, as something like this. Okay, so the remainder is being in the state of triaxial stress. We discussed this again before. So the effect of this type of end restraint is to basically give an apparently higher strength than the true compressive strength of the specimen. All right. So as we can see here, the different failure modes, depending on the condition of the end restraint. Okay, as you can see here, this is basically where we have confinement on both ends. As you can see, this area and lateral confinement, and this area also, we end up with this shape of failure. This one here, confinement in one end and without a confinement on the other end, we get this shape. And this is like a split in failure, no confinement on either end. We end up with this shape of or mode of failure. Okay. So the apparent strength will increase as the relative volume of the specimen subjected to the lateral restraint increases. Okay. For example, like in this case. So this accounts really for the apparently higher strength of cylinder with length to diameter ratios less than 2. So it also accounts for the fact that in general cubes indicate higher strength than cylinders, because cubes simply are not long enough for the effects of the ends of the end restraint to die out. Okay, we said the longer the specimen is, the effect, as I mentioned, the effect of that end restraint is about square root of 3/2 of the diameter. So the longer the specimen is, okay, the effect will die out quickly, quicker, or will be eliminated. In the case of the cube, it's not long enough really for that effect to die out. So for a given specimen geometry, the higher confining stresses will also result in higher apparent strength. You remember, the reason really to know this, when you compare test results, you have to know how they were tested, cylinders or cubes. And the cylinder, have they been tested by a standard ASTM C39 cylinder, or they were tested using some other cylinder? And again, you have to be aware of the test, how the test was carried out. Okay. Okay, so also it should be noted that if a very soft material is placed between the ends of the specimen and the platings, to eliminate friction, the outward flow of the material under pressure may induce lateral tensile forces in the ends of the specimen. This will reduce the strength of the specimen, and it may fail by vertical splitting, as we've seen here. Okay, and it is this the usual case, however, that friction reducing materials are unable to completely eliminate the effects of the confinement. Okay. On a more fundamental level, though, to speak at all of compression failure of concrete or most material, it is incorrect, since compression tends basically to squeeze atoms and molecules closer together. So it is hard to see how pure compression can lead to failure. So in compression tests, there are also secondary tensile stresses induced in the specimen, basically at right angles to the axis of the specimen. Since concrete is relatively weak in tension, it is these stresses that cause cracking and failure. We talked about this again. So it has been suggested that the failure of concrete in tension will occur at limiting strain of about 0.0001 to 0.0002. Okay, for ordinary concrete, with Poisson's ratio of approximately 0.2, such lateral tensile strains will occur at a fairly low compressive loads, and this could be the cause of failure, as shown in this case here. Okay, this is properly the natural mode of failure in a pure compression. The stresses induced due to end restraint may cause an apparent conical failure of the specimen, as indicated in, oh man, I went too fast. This figure A, I'm sorry about that. Okay, so we can, since basically we cannot avoid some end restraint, it is likely that the failure occurs through some combination of forces, as basically shown in this case. Okay, so tensile cracks may not be able to propagate, through the portions of the specimen under lateral confinement. Okay, so basically that is the case that may more than likely occur in real life, because we have a combination of both cases. Whatever we do sometimes to eliminate that confining pressure to get real, the sense of the apparent strength, but since we cannot eliminate it totally, we do not get this type of failure, we get this failure. Okay? The second factor is the test apparatus. Okay, for the test apparatus, as well as being plane, the ends of the specimen should be perpendicular to the axis of the specimen. Since this is, very difficult to achieve exactly, a spherically seated platen is used. A small deviation from parallelism will then not, affect the strength a lot. The ASTM C39 specifies that the spherical head should be lubricated with conventional oil rather than, the pressure type grease, so that, once the head is in full contact with the specimen, further tilting will not occur. Okay, so changing the degree of lubrication on the spherical seating can cause apparent changes in strength. Okay, this is for you in order to know, for example, how the tests are done and what goes into the testing. Different type of platens can be, can also lead to different results. Since even, steel platens will distort slightly under load. Platens of different stiffnesses will lead to somewhat different stress distributions across the ends of the specimen. That's something also to bear away. Okay, again, these factors probably will not affect you at all, as long as when you compare test results, you are comparing them on a consistent basis. Okay. The type of testing, head that properly best approximates true uniaxial compression is that what we refer to as brush plating. This basically consists of filaments about 5 by 3 millimeter in cross section, with gaps about 0.2 millimeter in between them. Okay, this basically allows the concrete to expand laterally with very little restraint. Such platens will, of course, give lower strength than these ordinary steel platens. Okay, and again, when you compare concrete tests, they have to be compared based on the same testing method and the same type of machine. Okay, also the testing machine themselves can vary in rigidity. So from basically relatively hard to relatively soft. This difference has been found to have, only negligible basically effect on the measured compressive strength. However, the very rigid machines will sometimes permit the measurement of at least part of the descending branch of the curve, of the curve, of the load versus deflection. We talked about this in the previous section, if you remember. Okay. The next factor is the length to diameter ratio. The standard cylinder has a length to diameter ratio of 2. Although, with that, as we have seen, this still produces considerable lateral confinement within the specimen. Okay, so it has been found that if the LD ratios are, other LD ratios are used, the specimen strength changes due to the end effects we described just now. So the general effect of the length to diameter ratio on strength, are shown in this figure right here. Okay, So as you can see here, this is the percent of strength of cylinder with an LD over 2. As we can see here, for example, 2, we're talking about 100%. This is 2, this is 2. The higher, we get lower strength. The lower, we get higher strength. And we talk about this basically has to do with the end restraint effect. But you know, the exact shape of this curve depends to some extent on the end conditions and the type of concrete tested again. So it has been found that high strength concrete is less affected by the variations in specimen geometry. So as a general rule, you know, for a specimen subjected to end restraint, an LD ratio of 3 is high enough to produce uniaxial compression, okay, up to 3. So in the center portion of the specimen without causing problems to slenderness, okay? So the effect of the length to diameter ratio, as again, is particularly significant when tests are carried out on drilled cores. You know, sometimes we do not only do compressive strength on newly cast specimens, sometimes we drill cores from an existing structure in order to evaluate it. So this effect of the LD, L over D, is more significant in the case of drilled cores. Okay. Sometimes, you know, the LD ratio is often less than 2 because we don't drill large cores or certain size. In this case, you know, correlation factors such as the table shown here, okay, are provided according, this is, you know, in pursuance to ASTM C42, so that, you know, the specimens with different LD over, you know, L over length to diameter ratios, can be compared on the same basis, okay? If the LD is greater than 2, the specimen can be cut basically to size before testing, okay? So this is, you know, for these cases, mostly, as I said, for the drilled cores, okay? The next factor we will talk about is the specimen geometry. Again, since different geometries of specimens, you know, cylinders or cubes give different values of strength, which specimen shape is then, you know, best? Clearly, cubes are somewhat easier to test since they require no capping. However, the tendency is to prefer cylinders to cubes, okay, especially in research, as there is a feeling that they better represent the strength of the concrete. But as we have seen, small concrete specimens do not particularly represent the strength of the concrete and the structure. So they give only comparative data. So it makes really little difference which specimen geometry is chosen, as long as they are used consistently. Remember the key magic word, okay? So both strength, you know, and the variability in strength of concrete decreases as basically the specimen size increases. Common sense. This is greatly explained by the weakest link theory. We talked about the interfacial zone, the weakest link. So that is, we assume that the strength of the concrete specimen is governed by the weakest link within it. So the larger the size of the specimen, the more likely it is to contain an element that will fail at a given low load. You know, such point of weaknesses are, in general, the types of flaws that were, you know, discussed in the previous module of the class, if you remember. But as specimens become larger, the differences in the distribution of the flaws within each sample become less at the same time. So the variability decreases as well. This figure here, right here on the screen, shows basically the variation in strength with cylinders with L over D of 2, but with different diameters. Okay, we maintained the length to diameter ratio, but basically we increased the diameter. That means we increased the size of the specimen. So this is the strength percent of the diameter of the 6 by 12 or 150 by 300 specimen, and here we increase the diameter. So as we increase, basically the strength decreases. Okay, so this is the effect of the size of the specimen basically. The next factor is the rate of loading. Excuse me. In general, the higher the rate of loading, the higher the measured strength. So the reasons for this are not completely clear. It may be that, some slow rates of loading allow more subcritical crack growth to occur, maybe. So by this leading to the formation of larger flaws and hence, smaller fracture loads. This could be an explanation. On the other hand, it may be that the slower rates allow more creep to occur, which will increase the amount of strain at a given load. When the limiting value of the strain is reached, failure, of course, will occur. More likely, the observed rate of loading effect is due to a combination of these factors, perhaps, other factors as well. But this is really what I have to say about the rate of loading. It's more complicated, but just that's all I have to say about this factor. Okay, but again, to obtain comparable test results, the rate of loading in practice must be maintained, within fairly narrow limits. And again, we're talking about consistency and comparing results of the same testing. We're not with different testing from different testing methods and different practices. Okay. The next factor is the moisture content. Okay, most concrete specifications, such as the ASTM C39, require that concrete be maintained and tested in a saturated state. So it has been found that concrete that has been dried shows an increase in strength. The reason for this are not really completely understood. It may have something to do with the change in the structure of the calcium silicate hydrate on drying, okay? Or it may simply represent a change in the internal friction and the cohesion on a macroscopic scale. So that is, moisture may have a lubricating effect, allowing, particles to slip by each other in shear mode easily. Okay, that could be the explanation. The lower compressive strength, of wet concrete may also be due to the development of internal pore pressure as loaded, as the specimen's loaded. Okay, for an oven dried specimen, the increase in strength is on the order of about 10 to 15%. This increase in strength appears to be reversible. Okay, as subsequent resaturation will return to the concrete to its original saturated strength. Okay. Okay, the next effect is the temperature of the sample. For reasons that also not fully understood, the temperature of the specimen, at the time of testing will affect the strength, as shown in this graph right here. Okay, so higher test temperatures will result in lower strength, even for concretes that were identically cured in standard conditions. And again, for reasons that's not really very clear, it is although likely that at least part of the effect is due to the loss of moisture from the specimen while being conditioned to the higher temperature. Okay, that could be a reason. Okay, but again, it's not very clear why. So based on the preceding discussion, it should be apparent that the compressive strength is neither a fundamental nor a uniquely defined property of the concrete. Okay, so its value depends very markedly on the method of measurement. Since compressive strength results are of value primarily on a comparative basis, there must be strict adherence to a standardized testing method. Okay, so, and again, just I repeat what I said. Following standardized testing methods, being consistent, being aware, and know of and to know of when and how to compare test results is really the key here in understanding testing and to make full use of the testing. Okay, so that's really what I have to say about compressive strength. I will stop here, and next lecture will be lecture number 35, and we will continue with the remaining tests, the tensile, flexural, modulus of elasticity, and the non-destructive testing. So until then, thank you for listening, and I will see you next time. Thanks.